Thank you very much for the introduction, and I'm very pleased for this opportunity. And as you can tell from the opening slide, in addition to my KTH affiliation, I'm also 20% at Linköping University in the lab of organic electronics. Today, the topic is cellulosic biocomposites. So what I'm primarily referring to here is composites with a polymer matrix, and I will try to talk about how we could exploit the nanostructure of such materials. So this slide is about let's say, the reinforcement that we could use for wood and cellulose composites. So if we start on the left-hand side, we have glulam type of materials where we basically bond planks together into beams. Then we have veneer used in plywood, but we can also impregnate the veneer to turn it into wood composites. So previously, it was very popular to impregnate with phenylformaldehyde and make very stable materials based on such composites. We can make composites from fibers. And on the right-hand side, you see the nanofibrils from cellulose, which make up the cell wall. So we tend to distinguish between wood and plastics, but of course, wood is a polymer material, and the cell wall of this fiber is quite interesting. It has cellulose fibrils in a molecular mixture of lignin and hemicelluloses, but the cellulose fibril is really what we're utilizing in composites, because this fibril consists of extended chain cellulose molecules. It has a modulus, the crystal has a modulus of 130 gigapascal, but so let's say we could achieve a effective modulus of 100 gigapascal. That's quite impressive for a polymer. So that's what we're going to utilize. I also want to emphasize the material science and engineering paradigm, which is essentially where I've been operating. And the essence here is that for composites, we start with constituents. So those are fibers, they can be modified, and we have a polymer matrix. And then we subject these constituents to some kind of processing operation. Melting, mixing of the components, some chemical reaction, and we can vary temperature, pressure, etc. So the first aspect of the science is really relationships between processing parameters and structure. So structure traditionally has been studied by microscopy, but of course with chemical products, you need all kinds of chemical characterization methods as well. And we can do this at different scales. And I would say that a very important parameter when we deal with the cellulosic materials is relative density, which is the same as volume fraction of solid material. And then this structure is controlling the physical and chemical properties. And my emphasis has always been on mechanical behavior. So I've been trying to understand how the microstructure influences material properties. So this is sort of traditional material science and engineering. And I think today we also need to add environmental aspects. And if we look at the material's life cycle, I think that becomes a little bit more clear. So on the left-hand side, you see the plant biomaterial that we're starting with. We extract the constituents. And if you look at that circle in the middle, we strive for low energy demand. Recently, there's a strong emphasis on green chemistry, try to be as eco-friendly as possible, low energy. We have shaping operations. Then we have service life. So let's say it's a component for a car. As long as the car is in service, the component is functional. We can reuse the component, and then the question comes, what happens after that? And previously we used a lot of landfill, but nowadays, of course, we need to consider recycling, which is very important in this context. So the fiber center that Annette is directing, plastic substitution with minimum chemical modification, is written as one of the objectives. I will try to keep that in mind here. Now, energy use is very important, and I'm very inspired by Mike Ashby's ideas. Essentially, he's arguing that as engineers, we need to adopt simple measures. We need things that are easy to understand and analyze. And when it comes to material selection, this is very helpful because the term he utilizes, embodied energy, which is essentially the energy you need to prepare your material, that can, of course, be translated to carbon dioxide emissions. In LCA practice, we tend to use the energy mixture, for instance, for Europe. So then we can translate energy to carbon dioxide emissions. If you look at this illustration on the left-hand side, you see the energy needs. We start with, for a thermoplastic, we start with oil derivatives. We use plant energy. We need transport. We have a production plant where carbon dioxide is emitted. And in the end, we end up with polyethylene terephthalate in this case, which has a certain embodied energy per kilogram. This is for different materials. And I think this is quite interesting. If you look at the polymers, they are essentially scaled with respect to their upper use temperature. So higher glass transition temperature, higher embodied energy. So polyethylene and polypropylene are reasonably low, but there's something like 70 megajoule per cubic meter, which is substantial. PLA is the lowest one, but not that much. So it's maybe 55. If we then move over to the far right, the hybrids, you can see that carbon fiber composite, glass fiber composites, they're up here, something like 130 megajoule per cubic meter. And then paper and cardboard are much lower. The lowest one are plywood, and then we go to the bottom right corner, we see hardwoods and softwoods. So that's essentially what it looks like. If we look at specific numbers, we see them here. So bio-based plastics, 55 megajoule per kilogram in primary energy. But what is interesting is that pulp fibers are actually quite low. You see 14 megajoule per kilogram for bleached kraft pulp. CTMP, which is a high yield pulp fiber, is something around 5 megajoule per kilogram. And then wood, of course, is lower than that. If you think about nanocellulose, we start with the bleached pulp and then we need a considerable amount of energy. So in many cases, nanocellulose is around 100 megajoule per kilogram, but it depends on which process is used. There's an interesting detail if you look at the standard there under the headline. This is used for instance, for furniture. It's based on photosynthesis and some fairly strong assumptions, but essentially 1 kilogram of wood takes up 1.6 kilogram of carbon dioxide. And the reason for that, of course, is that the tree will emit oxygen as well. So that's taken up from air, but not included in the wood material itself. But this is normally not taken into account. But of course, this is very important for carbon dioxide emissions. So let's look at the cellulosic composites. I mean, the basis needs to be the fiber properties. And I think it's reasonable to try to compete with glass fiber composites. You look at the upper row there. 2.6 gram per cubic centimeter, modulus of 76 gigapascal. And there you can see that flax fibers compete very well. Wood almost as high, at least the potential is there. And of course, the density is much lower. And then if you look at tensile strength, glass fibers are stronger. And the main reason for that is actually that, first of all, we have the microfibril effect for plant fibers. If you look at the cell wall there below the Young's modulus column, the main S2 layer in wood has a certain microfibril angle. And if that angle is small, then we have the modulus approaching 60 gigapascal, especially if we also remove some lignin. So this is where the variation comes from. And also, we tend to damage the fibers during processing. And that's why the range for strengths is quite large in the right-hand side column there. So that's our challenges. So we need to be kind to our fibers in order to utilize the plant fibers fully. I also wanted to show an overview of the processing approaches. By far, the most common processing of plant fiber composites is melt processing, and it's on the left-hand side there. But that is actually limited in many ways, but it's rational, it's dominating in the automotive industry, for instance. And you can see our reference there, polypropylene, 40% by weight of glass fibers. It has a typical modulus of 10 gigapascal and the strength not of 100 gigapascal, but megapascal should be the accurate number there. Then you see in the next column, mixing casting is a possibility. If it's nanocellulose, it's not a good idea because we will have lots of agglomeration in most of the cases. I will talk a lot about liquid molding, which is a dominating process for advanced fiber composites. So essentially you have a network and then you impregnate with a monomer or prepolymer and then you polymerize. And the advantage is that you can reach very high volume fraction if you use this approach. And solvent casting is common in the literature, but it's not very practical. So let's start with nanocellulose. We prepare nanocellulose from pulp fibers. In our group, we've worked a lot on hollow cellulose because this way we use mild parasitic delignification, and in this way we preserve the original molar mass of cellulose, and we have a high hemicellulose content, which is often advantageous. I would say that for materials, the main applications of nanocellulose is in coatings, adhesives, and films devices. The original hope for bulk materials turned out not to be very feasible. So really, this is where the focus is. So I wanted to start with this example. Here we can use a paper making approach, and the idea is simply to control the polymer matrix distribution. So we have a colloid of nanocellulose, and then we sorb, in this case, starch, amylopectin starch. We do it in two different ways. On the so-called mixed method, we just mix them. In the lower method, the core shell method, we deliberately sorb the amylopectin to the surface of the fibrils. And if you look at the micrographs, you see the core shell column. It's a much more uniform distribution of the cellulose, and it's much better covered by the polymer matrix because we essentially put it there from the beginning where it should be. If we just mix it, we will have inhomogeneous distribution of the polymer matrix. This results in improved moisture stability of such materials. If you look at on the left-hand side, you see that at 85% relative humidity, you have the same properties by using between 15 and 23% of starch. You have the same film properties as you do for the original CNF film. It's even better for one of the composition, and I'm pretty sure that's because there is some porosity in the original CNF film. If you just mix them, the starch and the nanocellulose, you suffer in properties because you plasticize the matrix at 85% relative humidity. So you reduce the properties significantly. So there's an image on the right-hand side of the image. You see the more well-organized core shell material. And in the mixed one, you will have larger sections of starch-rich material. The final example of nanocellulose is this filtration of CNF and clay nanoparticles. But in this case, we also impregnate with epoxy. And if you look on the right-hand side micrographs, you see at the scale of 1 micrometer, the upper image, we have some heterogeneity. And if we go down to the lower micrograph, 200 nanometer, you can see that the scale of the heterogeneity is roughly a few hundred nanometers. So we have matrix-rich region, we have clay-rich and nanocellulose-rich region. So it's not perfect, but it's the fact that we have an epoxy resin makes this material very stable against moisture. So the left-hand side image for this hybrid composite, you see that if the total reinforcement content, so C1M1 means that we have the same amount of cellulose and clay. So we improve strength significantly, and then there is some improvement when we go to higher reinforcement content, but not as strong as in the small amounts of nanoparticles. But the key thing is really the oxygen permeability. If you look on the right-hand side there, you see very strong effect from reinforcement content. So these clay platelets are really efficient. And the fact that we use epoxy in combination with these materials means that we get down to very low oxygen permeability levels, and it's not sensitive to moisture either. I wanted to say something about melt processed composites because they are industrially so important. It's very difficult because of agglomeration problems to use nanocellulose here. The best work has been done by Jan at Kyoto University. He has by far also had the largest resources. So his idea is that he takes pulp fibers which have been pre-treated, and then he carries out melt compounding so that the pulp fibers disintegrate and form smaller fibers and provide more efficient reinforcement. The limitations is that he cannot use very high fiber volume fraction because then the viscosity goes through the roof. So actually what he's doing more recently is that he's looking into pulp fibers to go for the Japanese automotive industry. But the limitations here are we cannot go to very high fiber volume fractions, and we will damage the fibers unless we have this clever technique that Jano is using. So for that reason, I will go to these liquid molding approaches. In addition, I want to utilize the wood cell wall. The disadvantage with nanocellulose is we first disintegrate the wood cell wall, and then we try to put it together again. We try to orient the fibrils, which is not that easy. If we could utilize the fibers, we can use the techniques which are already here for orienting pulp fibers. And if you look at the right-hand side image there, you can see that the fibrils can be nicely separated by chemical treatment. And we already have the fibrils aligned in such fibers. I think this is perhaps one of the best examples I can think of. This is work done together Anna Sjöstrand and Farhan Ansari were PhD students of mine and Lars Berglund. If you look on the left-hand side, we're using sulfite fibers. We simply wanted high cellulose contents. It's 96% cellulose. Anna oxidized these fibers, and if you look on the right hand, well, the blue, you see the two fibers compared, and oxidation swells the cell wall, so the fibrils in the cell wall become more separated, and this facilitates the impregnation of epoxy. That's really the idea. So if you look on the right-hand side, the green background images, the unmodified structure is more collapsed. It's much more difficult to impregnate with the resin. You see the central lumen region of the fibers tend not always to be filled. If you look at the cell wall, certainly you're not going to fill the complete cell wall with epoxy. Whereas on the right-hand side image, you look at the micrograph in the bottom right, it has really great fiber matrix integrity, and we also have polymer in the cell wall. And this really improved properties. So if you look on the left-hand side, mechanical properties are better for the swollen cell wall, despite the fact that we have 18 weight% fibers in all these three cases. But there's a substantial improvement if you manage to swell the cell wall. And the interesting thing is that when we manage to get epoxy into the cell wall, we stabilize the material against moisture. So if you look at modulus data on the right-hand side diagram, you see that with no oxidation, the staples on the left-hand side, you see a significant drop from blue to red when we expose it to 98% relative humidity. But with the oxidized fibers, there is a minor decrease because the cell wall is impregnated by epoxy. One problem is to reach high enough volume fraction of fibers. So this is all data from a student I had in Luleå. He took regular paper, and you can see, even though this is also oriented paper, it's quite sparse. We have a lot of matrix regions here, and the properties are limited. Although the fibers are oriented, we only have 8 gigapascal modulus in the fiber direction. So what can we do to increase the fiber content in pulp fiber composites? One possibility that we've explored recently is to hot press fibers. This is interesting by itself. You can make molded fiber type of materials with high fiber content. Typically, we can achieve a porosity of about 20%. You see on the image of the processing route there, we use a dynamic sheet former. But I think in liner production, for instance, you also have substantial orientation, and that's not so far away from dynamic sheet forming results. We then hot press, and we utilize the lignin in the cell wall of unbleached fibers. So the lignin hemicellulose mixture functions as a liquid binder in these materials. And if you look at the micrographs, you see the nature of the material. It's fairly dense. But in the lower right corner, you also see that there is void space. We don't manage to close all the voids. So there is a porosity of about 20%. We reach fairly good properties here. 20 gigapascal, we can make laminates by putting oriented layers together. And the failure process is gradual. If you look on the right-hand side, you see early fiber fractures, but there is no catastrophic failure. That takes much longer time. And then we see, just before the end, we see that individual fibers have been fractured. But this is a good starting point for making composites. We already have high fiber volume fraction. So then I switched to more eco-friendly composites. In this case, we have a bio-based acrylate matrix. This is work by Peter Olsén. And the idea is he uses limonene oxide. Céline Montanari did this in her thesis. And you combine it with acrylic acid, which is now available from bio-based resource. And we combine this bio-based acrylate and we impregnate hot-pressed wood fibers. If you look at in the lower right-hand side corner for the micrograph there, you see it's reasonably well dispersed, but there are still some voids that we could not penetrate. You can also note that this material is reasonably transparent, which is a good sign. If you do an LCA analysis of this material, it turns out that the polymer matrix completely dominates. So if we're going to do something about the environmental footprint of composites, we really need to work on the matrix phase. Minimize the amount of matrix and try to have lower impact from the polymer itself. This material is reasonably good. If you look on the left-hand side, you see the hot-pressed fibers stress-strain curve. And with 50% fibers, which is an achievement in itself, we get a modulus of 17 gigapascal for oriented fibers. And the strength is limited because of the brittleness of the polymer. If we compare on the right-hand side with PMMA, which is an excellent polymer matrix if you manage to get high molar mass, you see that we have similar modulus when we use, this is holocellulose fibers, but the strength is much higher. And one reason is that we can go to much higher strain because the polymer is not so brittle. So that's something to work on. One of the major problems with fossil-based plastics is that chemical recycling is virtually impossible. The chemical industry has long argued that that should be possible, but there is no progress. If you try to do chemical recycling of an existing fossil-based hydrocarbon polymer, you end up with a mixture of small molecules which can only be used as fuel. There's no way you can use it for chemical products because the polymers were simply not designed for this purpose. So Peter Olsén's idea is to design recyclability into the polymer matrix from the very beginning, and he tends to, so far, to use ester bonds. So in this work, where also Céline Montanari, Erfan Oliay, and Phil Josephson have been active, the idea is to use PLA. And it's a pre-polymer, and this pre-polymer is designed by Peter. So you can see in the upper row there, you see he starts with lactides, and then he combines it with the Pastor product, which is bio-based, and creates a module which has one part has hydroxyls and another one has acid groups. So then you can carry out esterification. The resulting polymer has a glass transition temperature of 50 degrees and low crystallinity. And that's deliberate because the aim is to facilitate chemical recycling. And then crystallinity, of course, is an issue. So this works out quite well. And the process is the following. You take the two components, just like in any resin, epoxy or unsaturated polyester resin. You do liquid impregnation of your, in this case, holocellulose spruce fibers, which have been filtered and used as reinforcement. You impregnate, you polymerize, and you can actually form it afterwards because the cross-link density is actually quite sparse. An interesting thing is that because of the carboxyl groups, there is chemical linkage to the fibers. So the hydroxyls on the cellulose surface reacts with the carboxyls in the matrix, and that's showed by the spectroscopy data. So it's an interesting possibility, although I think the key here is really the chemical recycling. The mechanical properties are okay. It's very stiff. You get 24 gigapascal at 50% fibers. But as you can see, this resin is also brittle. If you look on the stress strain curve on the left-hand side, you see the hot pressed fibers have much higher strain to failure than the composites. And that's because we're still battling the brittleness problem of the material. But this is a very good start. And the properties, I mean, 24 gigapascal, that's high modulus material. As you can see from the photograph, this material is optically transparent. The micrograph is very interesting because you see the main challenge with these composites. It's really difficult to impregnate the lumen, the interior of the fiber. So that's where we're struggling at the moment in terms of processing ability. It's very easy to recycle this, and we are able to do this at low sodium hydroxide concentration, 0.4% room temperature. And the remarkable achievement compared with what is in the literature is that it's possible not only to reclaim the lactic acid, which is a monomer that can be reused, but also the fibers. Under such mild conditions, there is virtually no chemical damage to the fibers. So they can also be recycled and used again for reinforcement. And I think this is very encouraging. So my final topic then is composites from wood. And as I mentioned in the beginning, this was done already in the 1950s, 60s with phenylformaldehyde impregnation. And formaldehyde, I don't think is a good. It's used, and but we should really try to find alternatives. So it is interesting to examine wood composites, to revisit wood composites. And the new element is that these days we are also carrying out delignification, mild delignification, which creates more space for monomer impregnation. And if you look in the upper right corner, you see the typical data that we can achieve depending on the wood content. We are in the range of 10 to 17 gigapascal typically. We can go higher if we compress it, but for veneer, those are typical numbers, and quite strong because the fibers are oriented in the right direction. I wanted to take the example of transparent wood biocomposites because it's actually very good when you're trying to optimize the nanostructure of the cell wall, because optical properties are incredibly sensitive to processing defects. So these are the challenges with transparent wood. We want to improve transmittance, and there are two main reasons for that. Refractive index mismatch. So this is a difficult issue because cellulose is birefringent, so it has two different refractive indices depending on which direction you measure in. And also fabrication defects will scatter light. So it's an example in the micrograph. You see interface debonding, which will increase scattering. The other problem is to make thick composites. You can imagine if you delignify wood, it's not uncommon that you make pulp fibers on the surface, whereas the core of your wood specimen is not treated at all. So how can we address this problem? How could we make thicker composites? Well, cell wall swelling should be the goal. And this was a bit of luck, I would say. The original ambition was to try to dissolve cellulose in the wood cell wall, which of course did not work because cellulose does not dissolve if you have lignin and hemicellulose right next to it. But the interesting thing is that when we used conditions for cellulose dissolution, 7% sodium hydroxide minus 6 degrees, we observed enormous swelling of the cell wall, much more than you normally see with sodium hydroxide at high temperature. And the reasons we think are related to the reasons why you can dissolve cellulose at low temperature. According to Björn Lindman's ideas, this is related to hydrophobic interactions, which may be important also in this case. You can see here that the cell wall thickness dramatically increases for our model material here. Specific surface area increases. You see below the staple diagram, you see surface charge and specific surface area values. One of the interesting details is that we actually managed to remove some of the lignin. If you look in the lower right corner, we lose hemicelluloses as expected, but there is also lignin disappearing, which is not expected. And I think that's an interesting aspect. So we managed to make thick sample, 1 centimeter. We then can delignify without any problems homogeneously. We acetylate in order to really reduce moisture absorption, and then we impregnate. And if you look at the micrographs where the arrows are, balsa has an almost perfect fiber matrix interface. It's more difficult to see for birch, but if you compare the two micrographs for birch on the right side, you can see that there is substantial cell wall swelling. And we were aided by Tom Wilhammar and his colleagues at Stockholm University, who did electron diffraction. And on the left-hand side, this is native wood PMMA. We have absolutely no polymer inside the cell wall, so it's all white from cellulose scattering, electron diffraction. On the right-hand side, we have sodium hydroxide treated wood PMMA. You have lots of dark areas because PMMA is inside. It's amorphous and it doesn't scatter electrons. So that's another proof that we're successful in this respect. The optical transmittance is the highest we've measured for transparent wood. The cell wall is swollen. We've done acetylation, and we continue to work on this problem. The blue diamonds, which have even better transmittance. So the lower the slope, the better the optical transmittance. So this is transmittance versus thickness. The blue diamonds there, it's sawdust, and it's a bit of a strange study, but they have reported better optical properties than we have. So, summary. By using this low temperature treatment, we can obtain very large cell wall swelling, and that is interesting for many other types of modification. If I summarize, I hope I've convinced you that in terms of mechanical properties, wood composites can really compete with glass fiber composites. I think it's a very interesting challenge for research and for industry to work on cell wall tailoring of pulp fibers and wood so that we can better utilize the nanocellulose in our existing bulk material, so to speak. The sub-zero sodium hydroxide method is very appealing, and we will try to continue working on that. And Peter Olsén's approach on bio-based thermosets for chemical recycling is very interesting for composites, and that's also worth continuing to try to increase the glass transition temperature, to try to learn how to balance recycling and durability in such materials. I think what's remaining is really improved processing methods, continue to work on moisture stability, because obviously that's a disadvantage with plant fiber-based materials. And for instance, in the automotive industry, this is very important. You cannot have large dimensional changes with changes in relative humidity and temperature. And recycling is obviously important for cellulosic materials. With that, I'd like to acknowledge funding from the different funding agencies, my co-authors, and also KTH colleagues. It would not be possible to work on polymer synthesis, fiber science in this way if it wasn't for all the colleagues at KTH. And this is an image of the biocomposites group, which is led by Junjun Lee. Thank you very much.
Thank you a lot, Lars, for a very nice presentation and very inspiring. That it's so much done, but still there are challenges out there. So now we will open up for questions, and I can see in the chat that we have one question from Olof Sandberg. Linda, can we see if Olof want to unmute or if you should read the question?
I have allowed you to talk, Olof.
Yeah.
Well, thank you very much. Can you hear me?
Yep, absolutely.
Perfect. Now, I'm not a researcher, so I understand a little bit about what you're talking about, but I work more value chain integrated in the packaging converting area. So I thought it was very interesting listening into your presentation, and was wondering if CPLA could be utilized and looked into for a food contact barrier regarding food packaging, if you know those kind of possibilities. I know that there's some applications approved when it comes to plates and cups and cutlery and so forth, but
I think from that point of view, there is probably not a problem, but I'm not sure that is the ideal application, because this polymer is sort of designed for degradation. So if you subject it to moist environment, you need to know the timing of those degradation processes very well in order to choose such an application.
Okay, then I understand. Well, thank you.
Yeah.
Thank you a lot, Olof. I also saw that we had a question from Jan.
I have now allowed you to talk, Jan, as well.
Yes, hello, can you hear me?
Yep.
Yes.
Yes. One question I had is, I guess to get less brittle materials, entanglement of polymers also will play a role in your considerations, and like the molecular weight, right? So I don't know if you have looked into like how one can control the molecular weight in composites and like characterize it, because I imagine that's a bit more tricky than if you just synthesize a polymer by itself.
Yeah, the main problem here is that this acrylic, the Plima acrylic, is a thermoset, and our dilemma here is a little bit that we have many criteria to meet. We need optical transmittance, we need to match the refractive index, and it's not ideal to have a large aromatic side group here. It helps refractive index, but it messes up the ductility of the polymer. So from that point of view, thermoplastics are of course more ductile, but then it's not easy to find polymerization process that is well suited for liquid molding. So maybe you can understand from my, I guess the main message is that there are many criteria here that we need to meet, and so that's really a bit of a challenge.
And one question regarding, like, for example, the catalysts, because I guess you cannot get it out easily, or is it any problem that the catalyst remains in the material?
Not really. I mean, this is for the acrylic, it's conventional free radical polymerization, so we're using peroxides, and they are not really a problem. An interesting thing is that you are quite limited when you want to run liquid molding processes in wood or pulp fiber composites, because the chemical environment is a nightmare. It's so heterogeneous, and you have moisture there, so there are not so many polymerization mechanisms that can operate, but one of them is free radical polymerization. It's actually quite suitable for that.
Yeah, that's quite interesting. I mean, I never worked with this kind of environment, so it's interesting to hear about that. Yes, I already had the second question, which was about, I think all the composites that you showed here were more based on physical interaction of the matrix and the fibers, correct? Like what's like your view on, like, for example, using chemical bonds in like some kind of these composites to make or to modify like the interface between the polymer and the cellulose.
So if you manage to get the polymer into, so if we compare with glass fibers and carbon fibers and any other synthetic polymer fibers, they are inert. We cannot get the polymer matrix into the fiber. So plant fibers are unique in this respect. We can swell the fibers and bring the polymer into the cell wall. And if you manage that, then there is no need for, I mean, chemical attachment between the polymer matrix and the fiber that's not going to make any difference. The key is to have this molecular scale physical mixing of fiber and polymer matrix.
Okay, so it wouldn't be like of any like I would say like it could not be beneficial that, for example, you have a reaction between your cellulose and the polymer, and then under certain conditions you can revert it and then like make it kind of recyclable this way. I don't know.
Yes, I think that's not a bad idea. It has been explored substantially for nanocellulose composites, because the nanocellulose fibril is not accessible for the polymer matrix. So in that case, people have worked on that concept, and there it makes more sense.
Okay. Thank you very much. Thank you for the talk.
Thank you a lot, Jan.
Can I just comment? I think regarding your first comment, Jan, Lars, isn't it so that the work by Peter Rosén, which is really interesting, I think, I mean, then one way that you manage the sort of the molecular weight problem versus viscosity, at least, to get in the polymer in the matrix is by having it branched like that. So then you have a higher molecular weight and still have quite low viscosity, etc. So there are ways to manage that also.
Yes.
Which I think was a really nice way to do it.
Yeah. Linda, do you have a question? Or do we see any other questions?
I see no other questions.
I can, just for curiosity based question, you have this sub-zero sodium hydroxide swelling. There are different ways to dissolve and swell cellulose. So what do you think it is possibilities to develop this swelling approaches even further?
So the attractive thing with sodium hydroxide is that it's a chemical well known by the forest products industry, so they're used to handle this. It's relatively cheap, and I mean, in some cases for the existing processes, they are using a small amount of sodium hydroxide, and they don't even bother to wash it away because it doesn't hurt the product in the next stage. So that's why that is interesting. It's so Peter Olsén has also worked on acetic acid, which is sort of a benign swelling agent. But I think this is really the key for using pulp fibers and being able to have them accessible for modification also in the interior. You really need to swell the cell wall.
Yeah, we have used different types of plasticizer in the center, and to some extent, I suppose they also go in and swell a little bit apart, but maybe not so much.
Yeah, I'm not familiar with
Right. But that was very interesting, and we are looking forward to the progress in this area. It is so much fun things coming out there, and I think the recyclability that is very well worth to continue to work with.
Yes, absolutely.
With that said, I think we can, if we don't have any more questions, Linda, do you have any pop-up questions or?
No, I don't see anything.
In that case, I would like to thank you a lot, Lars.
Thank you.
Maybe next time I see you, I can give you a fiber bottle. And also that both on behalf on FibRe and Treesearch, thank you for taking your time and prepare this nice presentation.
Thank you very much.
Thank you so much, Lars. Very interesting.
Thank you.